Yay! All right, so we have the integral of root x plus 4 over x dx. We want to see if we can find a way to go about getting this integral. So any thoughts on a good way to start? It's not a rational function, right? So that first off, we don't want to do any of the rational function stuff to start with.
Could we say that x equals tangent squared, or 2 tangent squared of theta?
X would equal 2 tangent squared of theta. That would give us a pretty unpleasant dx. We could, well, I don't know. Let's try it. Let's see how that'll work out. That's not how I was planning on doing it, but.
Or I think 4 tangent squared theta, because it would be.
That'll probably be better. 4 tangent squared theta would make more sense. 4 tangent squared theta. All right, that's a reasonable thing for us to think about trying to do. So yeah, it's not a bad idea. So x is 4 tangent squared theta. Let's see what happens. Dx will be what? Should be 4 times the derivative of tangent squared, which should be 8 tangent theta, times the derivative of tangent, which should be secant squared theta, d theta. Everybody agree with that? Making sure I did my derivative right.
Yeah.
Okay. And so then that would end up giving us an integral of the square root of 4 tangent squared theta plus 4 times our dx, which is 8 tangent theta secant squared theta d theta, all over our x, which is 4 tangent squared theta. Oh, yeah, I think that might work out pretty nicely. So let's see what we end up with here. First off, we can take out the 4, right? If I take out the 4 from the square root, that becomes a 2 times the 8 is a 16. Divided by the 4 is a 4. So we can put a 4 out in front. And then we're going to have an integral of, and this is going to become, it's not going to work out as nicely as I thought. Maybe it will, we'll see. Tangent squared theta plus 1 inside of there, which is just going to be secant squared theta, which will become a secant theta when we take the square root. And it'll become a secant cubed theta. So we're going to have a secant cubed theta in the numerator. And in the denominator, we have a tangent over a tangent squared, so we should have a tangent. Everybody good with that?
Indeed.
Okay. And so then, let's see, we could simplify secant cubed over tangent a little bit. We could turn those into sines and cosines, right? So that would become 4 times the integral of sine cubed over cosine. Oh, sine cubed. That's not sine cubed. 1 over cosine cubed, sorry. Over sine theta over cosine theta d theta, which will give us what? 4 times the integral of, if we flip that around, that's going to give us a what? 1 over sine theta cosine squared theta d theta. Any thoughts on that?
Nothing productive.
Yeah, nothing productive. I didn't think so. What a shame. That was very sad because it was very promising. What we would need, and there's a nice simple way to do this. What we need is Weierstrass substitution, but we haven't learned that yet, so we can't do that. Oh well. This didn't work out very nicely. It was a good thought. And now, unfortunately, I'm going to have to just get rid of all of that hard work we did. So that didn't work out. That's the way it goes with integrals sometimes. Anybody have another idea?
Wait, I just have a question on that strategy we just did.
Yeah.
So we got four tangent squared theta. But I thought like the inverse substitution thing that we wrote is x equals a tangent theta.
Yeah.
So
That was when we had like an x squared plus something inside of there, but I think Noah just wanted to get something in there that would square root when we factored out the 4, so he chose to do the tangent. He chose to make it a tangent squared so that it could turn into a secant squared inside the square root. Because normally that's an x squared plus 4, right? Not just an x plus 4.
yeah. So you can just put whatever you want in there. It doesn't have to necessarily follow like the square root of a.
Yeah, I mean, you can try whatever substitution you want. It just might not work.
The way
Now,
I
it's
was
possible that it might have worked out nicely. These trig functions might have simplified down to something pretty straightforward, and we could have been okay. But didn't happen to work out that way. So
the way I was
Okay, I
thinking of
see.
it was that root x
sorry, say
squared.
that again.
The way I was thinking of it was like instead of x squared plus a squared, like root x squared, which would just be x.
Right.
Then it was like root x equals a tangent theta, so 2 tangent theta, and then x equals that squared.
Right. Yeah, it makes sense. I understand what you were thinking. And it was reasonable. It was a reasonable thing to try. That's the fun thing about integrals, is that there's something reasonable that makes sense, and then you try and do it, and then you're screwed, and you got to start over again. It's like a puzzle.
Could we try a U sub?
Sure, we could try a U sub. What do you want to U sub?
X plus 4, and then x at the bottom would become U minus 4.
Okay, so just the x plus 4?
Yes.
Okay, let's see what we can do with that. If u is x plus 4, du is just dx, right? And x is then going to be u minus 4. So let's see what happens if we do that. We have an integral of root u over, root u du over u minus 4. Okay. Now what?
I don't know. I was just asking if it was possible.
Yeah, certainly it's possible. We just did it.
Maybe separate the bottom because wait, oh no, we can't.
Can't
Or
separate.
actually, if we can we do like a difference of squares? Because that's you can do root u.
You can only do the partial fraction stuff if it's linear pieces or quadratic pieces that are irreducible or irreducible cubics. It's got to be a rational function to do partial fractions, if that's what you're getting at.
Oh, I don't know. I just thought the bottom was factorable and we can do something like that. I don't know. This probably won't work out then.
I mean, the bottom is factorable, but you can only, factoring, it's not going to do anything for us unless we could separate it into multiple different fractions. But you can only use the partial fraction decomposition method to separate it into separate fractions if you have irreducible linear or quadratic factors. So we could factor it to root u plus 2 and root u minus 2, but then there's no way to separate that into those other fractions. I mean, there is, but not in any way that's going to be helpful to us. I think we've hit another dead end. Next.
I don't know if this actually works out, but the only other method I can think of is by parts. We could do root x plus 4 times 1 over x and then do it that way. And make
Okay, we
dv,
can give that a try if you want. Sure.
Yeah, dv is 1 over x, and then v would be ln absolute value, right? Yeah.
Okay, and then what would your u be?
The root x plus 4.
Okay. And your du will be 1 over 2 root x plus 4?
Yep.
All right, and so what should we get?
We do the, what is it? uv minus the integral of v du.
This should be root x plus 4 natural log absolute value x minus the integral of natural log absolute value of x over 2 root x plus 4 dx.
Oh,
That's a fun sound. Oh, yeah. Oh, right. Huh? This is going to be a little bit of an issue to try to integrate that piece natural log of the absolute value of x over the 2 root x plus 4. I mean, we could try to do it by parts again, right? But so I think maybe not. Any other thoughts?
U equals square root of x plus 4.
No, Derek, we shouldn't do that new thing. Sorry, Derek was saying something in the chat. So sorry, somebody said something else. What did you say?
U equals square root x plus 4.
Okay, let's try that. U equals square root x plus 4. So if we do that, then what's du going to be? It's going to be 1 over
2 root x plus 4.
yeah, du is going to be 1 over 2 root x plus 4. And what is x going to be? Sorry, dx. What is x going to be?
U squared minus 4.
It might be easier if we just replace the dx. So maybe we don't want all of this. Maybe we just want to say dx is equal to 2u du. Yeah. In which case, we'll just go in and replace this as a root x plus 4 is a u. And then dx is 2u du. And x is u squared minus 4. How do we feel about that? Does that look better than before or no?
Yep.
I think that does look better than before. So now we've got an integral of 2u squared du over u squared minus 4. And now it's a rational function. And so how do we integrate a rational function? First, we look for a simple u sub or a special case, and then we look at the degree of the numerator and denominator. And since they happen to be the same, we should do
Division.
long division. U squared minus 4 into 2u squared plus 0u plus 0, which ought to give us a 2 here, and a 2u squared, and a 0u, and a minus 8. And when we subtract that, ought to give us a positive 8. So this should now become an integral of 2 plus 8 over u squared plus, u squared minus 4, not plus 4. How do we feel about that? Pretty good. Giving us 2u plus 8 times the integral of du over u squared minus 4. And how do we integrate u squared minus a squared? That was one that we were supposed to memorize, or no?
It's 1 over 2a natural log x minus a over x plus a.
2a, so 2 times 2. Natural log absolute value of our x, or in this case u, minus a over u plus a. That's our constant. And so we should then be able to just go resub in all of our root x plus 4s. 2 root x plus 4, and then plus 2 natural log absolute value root x plus 4 minus 2, root x plus 4 plus 2, plus our constant. Get it or no?
Was the I'm sorry if I can't remember it super clearly, but the thing that you just did with natural log was because of trig substitutions?
No, we did that. We proved this, that the integral of dx over x squared minus a squared, or du over u squared minus a squared, was equal to 1 over 2a natural log absolute value u minus 2 over u, or u minus a over u plus a, using partial fraction decomposition. So we broke that down into its difference of squares, u plus 2 and u minus 2, to originally prove it. And then we did the partial fraction decomposition to show that it comes out to be this.
Okay. I will look back in my notes.
Yeah, that's one that it just is helpful for you to just know. But it can always be done, since this is easily factorable into two linear pieces. You can always, if you don't remember it, just break it down into u plus 2, u minus 2, do the partial fraction decomposition, and then integrate from there. Good or no? Any questions, issues, problems with that? So we see that we may be presented with some integrals, and you might have seen a couple at the end of the homework last night where they just are a little different than things that we've just done and seen and know immediately what to do. And you just kind of got to try some stuff until you come across something that nicely works out. Sometimes it's just a u sub that then turns into a partial fraction, or sometimes you do a partial fraction and it'll turn into something that you can u sub and figure out, or it might be a trig substitution. There's lots of different options. Just work through it, try different methods until you come up with something that works. Okay. Good or no? All right. So we're not going to do any problems here with these. Might start one of them off and not really finish it, but we're going to talk a little bit about one other important method, and that is called a Weierstrass substitution. And that's what these are. So if you come across a function that you're trying to integrate, so if you have some integrand that is a rational expression, but all in terms of sine and cosine. So for example, something like this, 1 over 4 sine x minus 3 cosine x. If those sine x's and cosine x's were not sine x's and cosine x's, but just like x squareds or x's, that would be a rational function. So if other than looking like it's got trig functions in it, if it were a rational function, you can always use these 4 substitutions to turn it into a rational expression in terms of u. Okay. And they all come from this initial substitution where u is equal to the tangent of x over 2, so the half angle of tangent. And so you should be able to see, if I were to say u is equal to the tangent of x over 2, and I make this angle, my angle x over 2, if the tangent of that is u, that'd make the opposite side u, and the adjacent side 1, it would make this side the hypotenuse root 1 plus u squared. Would you guys all agree with that? Yes, no, maybe?
Yeah.
Okay. So from there, you should be able to figure out what sine x is and what cosine x is, and then also what dx is. So to find what sine x is, well, we don't have x, but we know that sine x could be rewritten as using a double angle to sine x over 2 cosine x over 2, couldn't it? Isn't that the double angle formula? Yeah, that's the double angle formula, right?
Yep.
Yeah.
Yep, okay. So if I were to try and plug all that in, I'd have 2, which is in my numerator, and I'd have the sine of x over 2, which is u over 1 plus u squared, square root. So that's my u in the numerator. And then I have a square root 1 plus u squared. And then my cosine is 1 over square root 1 plus u squared. And so those two square roots of 1 plus u squared in the denominator just become a 1 plus u squared in the numerator. Good or no?
Why are we using a double angle? Oh wait, because x is twice of. I see now. Cool.
Exactly. And so what could I do with cosine x? How could I find cosine of x?
Using one of the 3 double angle identities for cosine. I don't know which one to use.
I don't know. Which one do you want to use? What does cosine of x equal if you pick one of them? Doesn't matter which one, pick one. They're all equivalent. Prove to me that you know at least one of them. Pick one.
Let's go with the cosine squared minus sine squared one.
All right, so cosine squared x over 2 minus sine squared x over 2. So what's cosine squared of x over 2? Well, the cosine of x over 2 is 1 over root 1 plus u squared. So that's 1 over 1 plus u squared minus the sine squared, which is u squared over 1 plus u squared. Put them together, what do you get? You get 1 minus u squared over 1 plus u squared, right? There's your cosine x. And how do we find dx? Well, if u is tangent of x over 2, then that means that what? That means that x is equal to 2 inverse tangent u, isn't it? If I just take the inverse tangent of both sides of that and multiply by 2 and take the derivative, dx should be 2 over 1 plus u squared du. And so there's where your sine x, your cosine x, and your dx come from. They all come from u equals tangent of x over 2 and using a little bit of right triangle trig. And like I said, these are called wire stress substitutions, and they will turn any rational function in terms of trig functions into just a rational expression. So we're not going to go through and do the entire problem, but we have a dx in the numerator, which is 2 over 1 plus u squared du. So we have 2 over 1 plus u squared du. And in the denominator, we have 4 times sine x. And our substitution for sine x was 2u over 1 plus u squared. And we had a minus 3 cosine x. And our cosine x was 1 minus u squared over 1 plus u squared. And what happens to that now?
Do the 1 plus u squareds get canceled out?
They should all cancel out, exactly. So that should just give us an integral of 2 du over 8u minus 3 plus 3u squared du. I already have the du written there. And so now what do we have? We just have straight up a nice, simple, easy, rational function that we can deal with. Okay? And so we should be able to go in and use one of our methods for dealing with a rational function to deal with this one. Okay? And so I think in this case, hopefully that thing would, and we're not going to go through and do it, but yeah, this will probably just, maybe a factor. I think it factors. Yeah, it factors out pretty nicely. So does it factor? 4 times. I think that bottom factors, and you can use partial fractions to simplify it. Yeah. it does. So does that make sense what you would do from there? Or no?
Yeah.
Yeah, I mean, what about 3u and u, right? And a +3 and a -1. Right, so you just do partial fractions on 3u minus 1 and u plus 3, and you do your partial fraction decomposition, and then you just solve it from there. And then you'd go back at the end, and everything would be in terms of u, and you just make this substitution where all the u's become tangents of x over 2. So this is not something on the AP test. This is not something you need to memorize, but it's something that I think it's important that you're at least familiar with and recognize that anytime you see a rational function using trig functions, you can make those substitutions. Just look them up. If you don't have them memorized, look up wire stress substitutions and do the substitution. You can integrate. So like, what about this one? Could we do the same thing with this? Is that a rational function all in terms of trig functions?
Yes.
Yeah, so couldn't we do the same thing? Couldn't we turn cosine x into 1 minus u squared over 1 plus u squared?
Yep.
And then turn the dx into 2 over 1 plus u squared du, and turn the sine squared into 2u over 1 plus u squared and have the 1 plus and simplify it down? We certainly could. And that sounds like a lot of work, right? So don't get too excited when you see these and be like, oh, wire stress substitutions, because sometimes there's an easier method also. If you just let u equal sine x and du is then cosine x, this one could be just the integral of du over 1 plus u squared, which is inverse tangent of u plus a constant, or inverse tangent of sine x plus a constant. So just because a wire stress substitution would work doesn't mean that it's the easiest way. So I might still give you something that is a rational function in terms of trig functions, because there might be an easier way to integrate it. So recognize that it will work, but there might be an easier way also. In the previous one, there was no easier way to do that. You have to do the wire stress substitution. But for this one, nice, easy use of it. Good or no?
Yes.
Yeah, no, maybe, yeah, good. Cool. All right. In that case, we'll move on to another little thing we're going to quickly talk about here. With any luck, you're familiar. Did we talk about the hyperbolic trig functions when we did derivatives or no?
I don't believe so.
Ah, okay, interesting. I thought maybe we might have. Probably didn't, because I was trying to fly through stuff. So there's these other trig functions that are called hyperbolic trig functions. So your regular trig functions like sine and cosine and tangent and all of that fun stuff, those all come from a circle, right? You know that the coordinates of the point on the circle are always equal to cosine comma sine and so on, right? Remember doing that with the circle? A long time ago when you learned about trig functions originally?
Yep.
Yeah.
Yeah, okay. Those, we just call them the trig functions because those are the ones that 99.9% of the population ever have to deal with, right? The 0.1% of the population that goes into like higher physics stuff or higher math stuff that has to deal with these other trig functions are the only ones that really know that these exist. We have these other 6 trig functions that are called the hyperbolic trig functions, and they come rather than from a unit circle, they come from what's called a unit hyperbola, and they have to deal with the area underneath or the area between a hyperbola and the x-axis is how they're developed. but I just want you to have briefly been exposed to what they are and what they look like, and the fact that they have integrals and they have uses. And so I'm not going to go through and do a whole big thing on this either because it's not on the AP test. But this here is called hyperbolic sine. This is called hyperbolic cosine. This is hyperbolic secant, well, without the squared. It's hyperbolic secant, hyperbolic cosecant, hyperbolic tangent, and hyperbolic cotangent. Each of them are pronounced in different ways. This is sinh, right? Hyperbolic sine is pronounced sinh. Hyperbolic cosine is cosh. This is sech, cosech, tanh, and cotanh. And so these all have, like I said, relationships between a unit hyperbola and its area between it and the x-axis. And they all have integrals. So the integral of sinh is cosh. The integral of cosh is sinh. No negatives involved with either of the sinh or cosh ones. And the integral of sech squared is tanh. The derivative of tanh is sech squared, right? It's very similar to what we had before. The only ones that end up giving us the negatives are the ones down here. The integrals of the cosech, sech-tanh, and cosech, cotanh give you negatives. So just be aware that these exist, and if you ever need them, you can look them up. They can be used just like we used our inverse trig substitutions. You can use some of these to simplify out integrals like this and put them in terms of hyperbolic trig functions. So there are, and I'm not going to go into it, but there are a bunch of relationships between the hyperbolic trig functions, similar to like sine squared plus cosine squared equals 1. There are, there are hyperbolic trig identities also that you would need to know if you're going to actually go through and do some of these. So let me see. One of the, like the most basic ones are, I haven't done these in a while. I believe it's, so hyperbolic sine, I believe, is equal to e to the x, e to the x minus e to the negative x over 2. Hyperbolic cosine is the opposite of that. It's just e to the x plus e to the negative x over 2 is the values that those come out to be. And then you could use those to figure out what hyperbolic tanh, because hyperbolic tangent is just hyperbolic sine over hyperbolic cosine, and hyperbolic cosecant is 1 over hyperbolic sine, and hyperbolic secant is 1 over hyperbolic cosine, and so on and so on. And you could use all of those to come up with the different trig identities that you might need. So one of them is hyperbolic cosine squared minus hyperbolic sine squared equals 1. And then you can rearrange that to find the other one. So that's the one that's similar to sine squared plus cosine squared equals 1. But the most important one is hyperbolic cosine squared minus hyperbolic sine squared is 1. So those are the basics of what those are. And they can be used to, like I said, simplify some of these trig identity ones that we've done before. Not trig identities, but trig substitutions ones that we've done before. And that's all I'm going to say about that. So if you're interested in that and planning on taking higher math somewhere sometime, go online and watch some videos about that. But that's good enough for today.